This is SpaceTime Series 27, Episode 81, for broadcast on the 5th of July 2024. Coming up on SpaceTime, a close-up look at lava lakes on Jupiter's volcanic moon Io. NASA's Mars Perseverance rover crosses an ancient Martian river. And is space tourism healthy? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New observations from NASA's Juno spacecraft are showing that Jupiter's volcanic moon Io is covered in lakes of molten lava. The new findings, reported in the journal Communications, Earth and Environment, are providing a fuller picture of just how widespread the volcanic activity really is on this ancient violent world. It also provides first-time insights into the sorts of volcanic processes at work there. The moon Io has intrigued astronomers ever since 1610, when Galileo Galilei first discovered it. Some 369 years later, NASA's Voyager 2 spacecraft captured a magnificent iridescent blue plume erupting into the velvet blackness of space. The image was the first time a volcanic eruption had been seen on another world, and it confirmed that Io was geologically active. Subsequent missions to Jupiter with more Io flybys discovered additional plumes, along with lava lakes and volcanoes. Scientists now believe that Io, which is slightly larger than the Earth's moon, is being stretched and squeezed by the gravitational forces of both its neighbouring Jovian moons as well as its massive host planet Jupiter. The constant stretching and squeezing causes internal friction, causing heat and turning Io into the most volcanically active world in our solar system. But while there are many theories on the types of volcanic eruptions across its surface, up until now there's been little supporting data. Juno flew by Io in both May and October last year, coming to within 35,000 and 13,000 kilometres of the moon's surface respectively. Among Juno's instruments getting a good look at this violent world was the Jovian infrared auroral mapper instrument, which is designed to capture infrared light not visible to the human eye emerging from deep inside Jupiter. It probes weather layers down to around 50 to 70 kilometres below the gas giant's cloud tops. But during Juno's extended mission, scientists are also using the instrument to study the Galilean moons Io, Europa, Ganymede and Callisto. And the new Io imagery shows the presence of bright rings surrounding the floors of numerous hotspots. Juno co-investigator Alessandro Mira from the National Institute of Astrophysics in Rome says the high spatial resolution of the infrared images, combined with the favourable position of Juno during the flybys, revealed that the whole surface of Io is covered in lava lakes containing caldera-like features. In fact, in the region of Io's surface with the most complete data, scientists estimate about 3% is covered by just one of these molten lava lakes. Io's flyby data not only highlights the moon's abundant lava reserves, but it also provides a glimpse of what may be going on deep below the surface. The infrared images show several of Io's lava lakes with thin circles of lava at the border, between the central crust, which covers most of the lava lake, and its walls. The recycling of melt is implied by the lack of lava flows on and beyond the rim of the lake. That indicates that there's a balance between the melt that's erupted from the lava lakes and the melt that's been circulated back into the subsurface system. Mura says this gives scientists an idea of what the most frequent type of volcanism on Io is likely to be, namely enormous lakes of lava where the magma convects. The lava crust is then forced to break up against the walls of the lake. That forms the same typical lava rings seen in the Hawaiian lava lakes. The walls on Io are likely hundreds of metres high, which explains why the magma is generally not observed spilling out onto the pateray, bowl-shaped features created by volcanism, and moving further out across the moon's surface. The data suggests that most of the surface of these Io hotspots are composed of a rocky crust that simply moves up and down cyclically as one contiguous surface due to the central upwelling of the magma. In this hypothesis, because the crust touches the lake walls, friction keeps it from sliding, causing it to deform and eventually break, exposing lava just below the surface. However, an alternative hypothesis suggests that the magma is upwelling in the middle of the lake, spreading out and forming a crust as it cools, which then sinks along the rim of the lake, exposing underlying lava. Principal investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says the science team are only now starting to wade into the latest results from the close flybys of Io, which occurred in December and February. And these observations are showing fascinating new information on Io's volcanic processes. Bolton says that by combining these new results with Juno's longer-term campaign to monitor and map the volcanoes on Io's never-before-seen north and south poles, the infrared map is turning out to be one of the most valuable tools to learn how this tortured world works. Juno executed its 62nd flyby of Jupiter, which included an Io flyby at an altitude of 29,250 kilometres on June the 13th. The 63rd flyby of the gas giant is scheduled for July 16th. We'll keep you informed. This is SpaceTime. Still to come, NASA's Mars Perseverance rover crosses an ancient riverbed on the Red Planet, and we examine whether or not space tourism is really healthy. All that and more still to come on SpaceTime. Well, as we reported last week, NASA's Mars Perseverance rover is continuing its exploration of the fascinating Bright Angel geological site in the Martian unit of Jezero Crater. Mission managers have now revealed that the car-sized six-wheeled mobile laboratory forded an ancient Martian riverbed in order to get to the site. Originally thought of as little more than a route clear of rover-slowing boulders, the Nativa Valleys has instead provided a bounty of geological features for the rover's science team. After detouring through a dune field in order to avoid the wheel-rattling boulders, Perseverance reached Bright Angel and its geological bonanza several weeks earlier than expected. The route change not only shortened the estimated drive time to reach the area by several weeks, but it also gave the science team an opportunity to find exciting new geological features in what was an ancient river channel. Perseverance is now in the latter stages of its fourth science campaign. It's looking for evidence of carbonate and olivine deposits in the Martian unit area along the inside of the Jezero Crater rim. Located at the base of the northern channel wall, Bright Angel features rocky light-toned outcrops that may represent either ancient rock exposed by river erosion or sediments that filled the channel. Scientists hope to find rocks different from those in the carbonate and olivine-rich Martian unit and gather more clues about Jezero's history. But to get to Bright Angel, the rover was forced to drive along a ridge next to the Nativa Valley's river channel, which, billions of years ago, would have carried large amounts of water that flowed into the crater. Perseverance's Deputy Strategic Route Planner, Evan Gracer, from NASA's Jet Propulsion Laboratory in Pasadena, California, says the rover started paralleling the channel back in late January, making good progress, but then the boulders simply became bigger and more numerous, making transit more difficult. What had been drives averaging around 100 metres per Martian day, or sol, frustratingly went down to just tens of metres daily. In the rough terrain, and without the help of the Ingenuity helicopter to scout ahead following the end of its mission, Gracer and colleagues used the rover's imagery to plan drives of about 30 metres at a time. To go any further on a given Martian day, planners needed to rely on Perseverance's auto-navigation system to take over. But as the boulders and rocks became more plentiful, AutoNav would, more times than not, determine that going was not to its liking, and it would instead simply stop, dimming prospects of an early arrival at Bright Angel. However, the team were also looking at a shortcut across a 400-metre-wide dune field in the nearby river channel. The team had been eyeing the river channel just to the north during their travels, hoping to find a section where the dunes were small enough and far enough apart that the rover could pass between. But it was going to be risky. After all, Martian dunes have been known to eat rovers in the past. And Perseverance also needed an access point or ramp to safely travel down to reach the riverbed. Eventually, the team found both. The science team were also eager to travel through the ancient river channel because that would have given them a chance to investigate ancient Martian river processes. With AutoNav helping to guide the way along the channel floor, Perseverance covered the 200 metres to the first science stop in just one Martian day. The target was named Mount Washburn. little more than a hill covered with some intriguing boulders. But it turns out some of those boulders had never been seen on Mars before. Perseverance Science colleague Brad Kaczynski from Western Washington University says the diversity and textures of the compositions at Mount Washburn was exciting, as these rocks represented a grab bag of geological gifts brought down from the crater rim and potentially beyond. Among all these different rocks was one that caught everyone's attention, a Toko Point. Just 45 centimetres wide and 35 centimetres tall, the speckled light-toned boulder stands out in the field of darker rocks. Analysis by Perseverance's SuperCam and MassCam-Z shows the rocks composed of the minerals pyroxene and feldspar. In terms of the size, shape and arrangement of its mineral grains and crystals, and potentially its chemical composition, the Toko Point is in a league of its own. In fact, some Perseverance scientists are speculating the minerals that make up a Toko Point were produced in a subsurface body of magma that is possibly exposed now on the crater floor. Others ponder whether the boulder was created far beyond the walls of Jezero and then transported there by swift-flowing Martian waters eons ago. Either way, the team believe that while a Toko is the first of its kind they've seen on the Red Planet, it won't be the last. After leaving Mount Washburn, the rover headed a further 132 metres north to investigate the geology of Tough Cliff before making the four-sol 605-metre journey to Bright Angel and the strange popcorn-textured rocks which we covered last week. This is Space Time. Still to come, is space tourism healthy? And later, we look at planet Earth as it reaches its greatest distance from the Sun, the constellations Regulus and Leo, and one of the biggest known stars in the universe, Antares. They'll be among the highlights of the July night skies on Skywatch. New research warns that billionaires buying a trip to space should be considering if their heart can take it. A report in the journal Frontiers of Physiology found that most research on the impact of space travel on the human body has been done with fit, healthy, highly trained astronauts in mind. But with the rise of space tourism among the rich and famous comes the new prospect of wealthy, unhealthy people taking to the edge of space and beyond. The authors use computational modelling to simulate how microgravity would affect a human with two different types of heart failure. They say microgravity does put pressure on the heart, and in people with heart failure, their modelling indicates an increased risk of pulmonary edemas, a condition where fluid accumulates in the lungs, making it difficult to breathe. They say one day space tourists may be able to send a digital twin of themselves into virtual space first in order to test how their bodies would handle it before jumping on a rocket for the real experience. This is Space Time. And time now to turn our eyes to the skies and check out the celestial sphere for July on Skywatch. July is the 7th month of the year in both the Julian and Gregorian calendars, and is named after the Roman Emperor Julius Caesar, who was born during the month. Before being called July, the month was called Quintilis, which is Latin for fifth. The addition of the months January and February brought an end to that. On average, July is the coldest month in the year in the southern hemisphere, which is experiencing winter, and also marks the time when Earth is at aphelion, its furthest orbital position from the Sun. Of course, temperatures, or more accurately seasons on Earth, aren't dictated by the distance from the Sun, but rather the length of a day, and hence the amount of sunlight a given part of the Earth receives, which is governed by the tilt of Earth's axis. Consequently, that's why July is on average the warmest month in the Northern Hemisphere, which is currently experiencing summer. This year, aphelion happens at 15:06 in the afternoon of July the 5th, Australian Eastern Standard Time. That's 1:06 in the morning US Eastern Daylight Time and 5:06 in the morning Greenwich Mean Time. During this year's aphelion, Earth will be 152,099,968 kilometres away from the Sun. That's about 5 million kilometres further away than during perihelion back in January. Over cosmic time, these dates change. That's due to variations in Earth's orbit such as eccentricity, as well as axial tilt and precession, which all follow regular cyclic patterns known as Milankovitch cycles. Eccentricity involves changes in how elliptical Earth's orbit is around the Sun. None of the planets actually orbit the Sun in perfect circles, although Venus and Neptune are the closest. Instead, they all have elongated orbits which vary over time. As well as that, Earth spins on an axis which is currently tilted at 23.4 degrees compared to the ecliptic, Earth's orbital plane around the Sun. But this angle of tilt also changes over time, influenced by, among other things, the distribution of the Earth's mass. And just like a spinning top, the rotational axis of the Earth also changes its orientation through a process called precession, changing its position in relation to fixed background stars over a 26,000-year cycle. Now, all these effects impact the amount of solar radiation reaching the Earth, and what time it reaches the Earth, and consequently the planet's seasonal and climatic patterns. Right now, the Southern Cross is at its highest point in the southern sky, and is pointing directly towards the southern celestial pole. The Southern Cross falls within the constellation Centaurus the Centaur, the half-human, half-horse of Greek mythology, and the creature is holding a bow loaded with an arrow. The Centaur's front legs are marked by the two pointer stars, Alpha and Beta Centaurus. At 4.3 light-years, Alpha Centauri is the second of the two pointer stars from the Southern Cross and is also the nearest star system to the Sun. The Centaur's back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster, visible with the unaided eye from dark locations. Globular clusters are tightly packed spheres containing thousands to millions of stars. They're thought to have all originally been born at the same time from the same molecular gas and dust cloud, or they're the cause of small galaxies which have been consumed by bigger galaxies through galactic cannibalism. Omega Centauri is about 16,000 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Omega Centauri is one of the largest and brightest of the 150 or so globular clusters known to orbit around our Milky Way galaxy. Centaurus was one of the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. Turning to the right or west, and you'll see the constellation Leo the Lion, just above the western horizon. Its brightest star is Regulus, or the Little King, located about 79 light-years away. Regulus, designated Alpha Leonis, is actually a 5-star system, organized into 2 pairs. Regulus A is a spectroscopic binary comprising a spectral type B blue-white main sequence star, some 4 times the mass and 288 times the luminosity of the Sun, and a faint companion star thought to be a white dwarf, the stellar corpse of a Sun-like star. Spectroscopic binaries are stars that can't be resolved by optical telescopes into 2 separate objects, and can only be separated by observing their individual spectroscopic Doppler shifts as they orbit each other. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive known stars are spectral type M red dwarf stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. So put all that together, and our Sun is a spectral type G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red dwarf stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which can be about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which can be 75 to 80 times the mass of Jupiter, or 0.08 solar masses. Located further away are Regulus B, C and D, which are dim main sequence stars. At the opposite end of the constellation from Regulus is the star Beta Leonis, or Denebola, the horse's tail. It's also a luminous blue-white star, about half as bright as Regulus, and the third brightest star in the constellation Leo. Beta Leonis has about 1.8 times the Sun's mass and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Delta Scuti type variable star, meaning its luminosity varies slightly over a period of several hours due to pulsations on its surface. Algebra or Gamma Leonis is a binary system with a visible third component. The two primary stars are located about 126 light-years away and can be resolved in small backyard telescopes. Both are yellow giants orbiting each other every 600 Earth days. The unrelated tertiary star named 40 Leonis is a yellow tinge star that can be seen through binoculars. The star's traditional name Algebra means forehead. Delta Leonis or Zosma is a blue-white star 58 light-years from Earth. Epsilon Leonis is a yellow giant some 251 light-years from Earth. And Zeta Leonis is an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and located to the south of the primary. The third and faintest star in the system, 35 Leonis, is to the north. Lota Leonis is a binary star system visible in medium-sized backyard telescopes. Located some 79 light-years away, Lota Leonis appears to be a yellow tinge star with two components orbiting each other every 183 Earth years. Finally in Leo, let's look at Tau Leonis. Visible as a double star through binoculars, it includes a yellow giant located some 621 light-years from Earth, and binary secondary star 54 Leonis, which is actually a pair of blue-white stars that are visible in small telescopes and located some 289 light-years away. The constellation Leo also contains many galaxies, including the spiral galaxy Messier 66, as well as Messier 65 and NGC 3628, which are known as the Leo triplet. Located some 37 million light-years away, the Leo triplet has a somewhat distorted shape due to gravitational interactions between Messier 66 and the other two galaxies, which are cannibalizing stars from Messier 66. Eventually, the outermost stars may well form a dwarf galaxy orbiting M66. Both M65 and M66 are visible in large binoculars or small backyard telescopes, but their concentrated nuclei and elongation are only visible in larger instruments. Other bright, well-known deep sky galaxies in Leo include Messier 95, Messier 96, and Messier 105. Messier 95 and Messier 96 are both spiral galaxies, each about 20 million light-years from Earth. Both look like fuzzy objects in small telescopes, but display their spectacular structures in larger instruments. M95 is a barred spiral. Another barred spiral, NGC 2903, is thought to be similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also about 20 million light-years away. The constellation also contains the Leo Ring, a cloud of hydrogen and helium gas orbiting two of the galaxies in the constellation. A gravitationally lensed object known as the cosmic horseshoe is also found in Leo. Above Leo, you'll find the constellation Virgo, the Greek and Roman goddess of wheat and agriculture. Virgo's brightest star, Spica, is visible above the western horizon. It's located some 250 light-years away. Spica is Latin for ear of wheat, which Virgo is holding in a hand. Spica, or Alpha Virginis, is the 16th brightest star in the night sky, and is both a spectroscopic binary and a rotating ellipsoidal variable, a close binary system whose stars are not eclipsing but cause apparent fluctuations in brightness because of changes in the amount of light emitting area visible to the observer. Spica's two main stars orbit each other once every 4 Earth days and are so close they're egg-shaped rather than spherical and can only be separated by their spectra. The primary is the blue giant variable Beta Cepheid star. It undergoes small rapid variations in brightness. These are caused by pulsations of the star's surface, thought to be caused by the unusual properties of iron at temperatures of 200,000 degrees in the stellar interior. It has about 10 times the Sun's mass and about 7 times its diameter. The secondary star in Spica is smaller than the primary, but it's still some 7 times more massive than the Sun and has 3.6 times the Sun's diameter. Turning to the north now, and the constellation Boötes, the herdsman or ploughman. There you'll see the bright orange-red star Arcturus, or Alpha Boötes, just above the northern horizon. It's a red giant located just 36 light-years away, a bloated, aging star some 7.1 billion years old, nearing the end of its life. Although not much more massive than the Sun, it's now expanded out to some 25 times the Sun's diameter and will soon puff off its outer gaseous envelope as a planetary nebula, revealing its white-hot stellar core, a white dwarf, which will then slowly cool over the eons of time. Another bright reddish-looking star, this time in the east, is the red supergiant Antares, meaning the rival of Mars, because of its appearance and location in the sky, which appears to be opposite of Mars in the sky. Antares is one of the biggest known stars in the universe. It's enormous, 18 times the Sun's mass, 10,000 times its luminosity, and 883 times the Sun's radius. As we mentioned in last month's Skywatch, were it placed at the centre of our solar system, its surface would extend out close to the orbit of Jupiter. Despite being some 550 light-years away, Antares is still the 15th brightest star in the night sky. Unlike the Sun or Arcturus, the death of Antares will be far more spectacular. Antares is destined to explode as a core collapse or Type II supernova. When it does so, sometime in the next few 100,000 years, it'll appear as bright in the Earth's sky as the full moon and be quite visible even in daytime. Antares has a companion star, Antares B, a spectral type blue-white main sequence star more than 7 times the Sun's mass and 5 times its diameter. Antares is the heart of the Scorpion in the constellation Scorpius. Below Scorpius is the constellation Sagittarius, the Archer, which points the way to the centre of the Milky Way galaxy. Sagittarius is commonly represented as a winged centaur, pulling back on a bow which is aimed at Arcturus. The centre of the Milky Way galaxy and its supermassive black hole Sagittarius A star lie at the westernmost part of Sagittarius. Sagittarius A star is about 27,000 light-years away and has some 4.3 million times the mass of our Sun. It was in July back in 2016 that the solar system's barycenter moved outside the Sun, where it will remain until 2027. A barycenter is the gravitational centre of mass of a celestial system. For example, in our Earth-Moon system, the Earth and Moon actually orbit each other around a common centre of gravity, a barycenter. Now, because the Earth is so much more massive than the Moon, the barycenter is always inside the Earth's radius. If it were outside the Earth's radius, the Earth and Moon would instead have been classified as a binary planetary system, like Pluto and Charon. The solar system's centre of gravity or barycenter is usually located inside the Sun's radius. After all, the Sun contains over 99% of all the solar system's mass. But actually, the mass of the solar system is orbiting around the solar system's barycenter, which means the Sun also has a very slight spiralling 12-year orbit around the barycenter. And every now and then, when the planet's orbital positions are just right, especially when Jupiter and Saturn are nearest each other, their combined gravitational interactions move the solar system's barycenter ever so slightly outside the Sun's radius. And because Jupiter and Saturn reach this alignment every 11 years, some scientists have speculated whether this could trigger the Sun's 11-year solar cycle. And before you ask, the barycenter isn't named after some guy in a beige safari suit called Barry, but rather it's the ancient Greek word for heavy or centre of mass. We also have 2 meteor showers, both of which peak in late July. There's the southern Delta Aquarids, which are visible from mid-July to mid-August each year, with peak activity on July the 28th and 29th. The shower originated either from the breakup of what are now the Marsden and Crack sun-grazing comets, or from the parent comet P96 Malkolts. The Delta Aquarids get their name because their radiant appears to lie in the constellation Aquarius, near one of the constellation's brightest stars, Delta Aquarii. There are two branches to the Delta Aquarids meteor shower, the southern and northern. The southern Delta Aquarids are considered a strong shower, with an average of between 15 and 20 meteors an hour between midnight and dawn. Listeners in the southern hemisphere usually get the better show because the radiant is higher in the southern sky. Since the radiant is above the southern horizon for northern hemisphere listeners, meteors will be seen to fan out in all directions east, north and west, with few meteors heading southwards, unless they're really short near the radiant. The northern Delta Aquarids are the weaker shower, peaking later in mid-August, with an average peak rate of about 10 meteors per hour. Meanwhile, the nearby slow and bright Alpha Capricornids meteor shower will take place from as early as July the 15th and continue until around August the 10th. The meteor shower has infrequent but relatively bright meteors and even some fireballs. It's generated as the Earth passes through a debris trail left by the comet 169P NEAT, which was originally identified as the asteroid 2002 EX12. However, it was shown to be weakly active during perihelion and was then reclassified as a comet. The meteor shower was created about 3,500 to 5,000 years ago, when about half of the parent body disintegrated and fell into dust. The cloud eventually evolved into Earth's orbit, causing a shower with peak rates of about 5 meteors an hour and some outbursts of bright flaring comets, radiating out from the constellation Capricorn towards the south. The bulk of the comet's debris won't be in Earth's path until the 24th century, by which time the Alpha Capricornids are expected to become a major annual meteor storm, stronger than any current annual shower. And joining us now is Jonathan Alley from Sky and Telescope magazine to continue the rest of our tour of the July night skies.
G'day, Stuart. Well, winter in the southern hemisphere is the season of the Southern Cross. This is the best time of year to see it, as it's nice and high up there in the sky, standing almost upright. Just look to the south. You've got a bit of clear sky. Just look to the south, and about halfway up from the horizon, you'll see it. Having said that, some people do have difficulty spotting the Southern Cross, and that's probably because it's quite small. It's actually really small. People look up in the sky and they expect it to be really big because they've heard of the Southern Cross, so it must be something big and prominent. But it's actually the smallest of all the 88 official constellations. It's really quite tiny. It is wonderful, and 3 of its stars are really quite bright. And those 3 stars are in the top 25 brightest stars as seen from Earth. So if you haven't seen the Southern Cross yet and you go out looking for it, just remember it's quite small, okay? And it looks, when we say cross, it's like a crucifix-type cross, not like a plus symbol on your keyboard. It's a crucifix-type cross, like a kite shape is the best way to describe it. Now, if you have a pair of binoculars or a small telescope, take a look just to the left of the leftmost star in the cross. And just beside that star, you'll see a lovely little small cluster of stars called the jewel box. And when you see it, you'll know why it's called that, as its stars do indeed just look like a handful of sparkly little jewels, and some of them are different colours. It's really quite beautiful. Even a pair of binoculars will give you a bit of a glimpse of that little cluster of stars. Further to the left of the Southern Cross are 2 bright stars, which are known as the 2 pointers, or the pointers, because if you draw a line joining them and then extend the line further on, it points more or less to the cross. So they point that way. So they're known as pointers because this thing of how do you find the Southern Cross? Well, the 2 pointer stars actually are really quite prominent. They're brighter than the stars in the Southern Cross, and they're quite close together. You really can't miss them. So if you get those 2 stars, the 2 pointers, and draw a line between them and keep the line going to the right as you're looking at it from this angle this time of the year, it sort of just clips the top of the Southern Cross. So that's an easy way to find it. One of those pointer stars, the one on the left, is the famous Alpha Centauri. That's the one that the Jupiter 2 in Lost in Space was trying to get to. I don't know how they could get lost so easily when it's the nearest star system to Earth. It's not that far away, really. They went wandering all over the galaxy, didn't they?
Well, it's in the southern celestial hemisphere, so these North Americans wouldn't understand it.
Oh, the pain. The pain. There was a fellow who took off from England once, and he just went, back in the old days when you're using a compass, and he just got his compass setting completely around the wrong way, and I think he was meant to be going to Europe, but he ended up in America, something like that.
Well, technically, what we call the North Pole here on Earth actually has a south polarity at the moment.
Well, that's right.
And the South Pole has a northern polarity.
Because on our little compass, the thing that's got N pointed on it, pointing the north, that has to be magnetically attracted to something that's got S on it, and vice versa. Yeah, exactly right. And you know, with compasses, you've got to be careful with compasses. So if you, let's say you're in North America, right? You've got a compass and you bought it in North America. Well, you've probably bought a Northern Hemisphere compass, and that is one that probably won't work in the Southern Hemisphere for one reason, and that is...
Really?
Look, it'll point the right way, but the problem is, well, it'll try to point the right way, but the problem is, if you've got a compass, everyone can sort of picture a compass in its little glass bubble, and it wants to point in the direction. But remember, if you're on the surface of the Earth and you're pointing your compass needle, let's say, towards the North Pole, and you're in North America, the North Pole, the compass doesn't sort of point in a curve around the Earth.
It points down.
Directly. It wants to point directly at the North Pole through the solid mass of the Earth. And what they do is they generally put a little tiny counterweight on the other end of the little needle. So if it points down, it's going to point down. It's going to rub on the scale, on the direction scale of the thing. So they need to keep it horizontal. So if you bring one of those down to the southern hemisphere, it's going to want to point north. It's going to dip downwards, basically, and scrape along the direction scale. And if you don't notice that, then you might think, oh, this needle isn't moving, therefore it's pointing it north. But the reason is it's not moving is that it's scraping on the scale. So you can have to tilt your compass a little bit to get that needle horizontal again. So there are northern hemisphere compasses and southern hemisphere compasses. So just be aware of that.
You're a font of all knowledge.
It's one of the things stuck in my head, and I wish more things would stick in the head, and I wish other things would go. Anyway, Alpha Centauri. Now, Alpha Centauri, when you just look at it with an unaided eye, it just looks like one star. But when you look through even a small telescope, you'll see that it's actually two stars, right? But in fact, it's three stars. The two stars are quite bright, and they're very close together. That's why they look like one star to the unaided eye, but through a telescope they look like two. There is a third tiny, faint, smaller one called Proxima Centauri, some distance away from the other two, which most people are not going to see. You need to know exactly where you're looking with a larger sort of telescope to spot that. But the interesting thing about that star, Proxima Centauri, is that it is actually the closest star to our solar system. It's just over 4 light years away. It's a fraction closer than the other two brighter stars that make up Alpha Centauri. Now, the Milky Way, which is our galaxy seen from the inside, you go out in the evening in July and you'll see it stretching across the sky from the northeast to the southwest. And if you've got some binoculars, it's all you need, a pair of binoculars and some reasonably dark skies. Take a look along the length of the Milky Way. You should see lots of star clusters and a few nebulae. Some places will be a little bit barer than others, but some areas of the Milky Way are just packed full of stuff to see, even with a pair of binoculars. Now, changing direction to the north, we were just talking about mainly the south, but turn to the north. One thing you'll notice if you live in a southern country such as Australia or New Zealand, that the northern half of the sky seems a bit bare at this time of year, at least part of it that we can see. But there are a couple of bright stars. There's one called Spica, which is the brightest star in the constellation Virgo. Everyone's heard of Virgo. And there's another star called Arcturus, which is the brightest star in the constellation Boötes, which no one's heard of, except for astronomers. Arcturus, the brightest star in that constellation, is actually the 4th brightest star in the sky, and Spica is the 16th brightest star in the sky. Now let's look at the planets. Venus is in the glare of twilight at the moment, low on the western horizon. You probably won't be able to see it at the start of the month, but by the last couple of weeks of July, it'll have risen a bit higher, and you should be able to spot it quite easily. So wait till the sun goes down, it's gone below the horizon. Look to the west, and the brightest light you see near the horizon there will be the planet Venus. So as I say, at the start of the month, it's going to be really low down and in the glare of the sun. But after the sun's gone down, in the second half of the month, you'll be able to spot Venus. Also in the west, but a bit higher in the sky, is Mercury, the innermost planet. And whereas Venus really stands out because it's bright, planet Mercury just looks like a little tiny, bright pinpoint star. Both of those planets will be setting within about an hour or two of sunset, Venus first and then Mercury second. And we have to wait for around about 10 p.m. for the next planet to appear, and that'll be Saturn, rising up over the eastern horizon. Saturn is fairly easy to spot because it looks like a fairly bright star and it's got a slightly yellowish tinge. Next up will be Mars, but you're going to have to wait till around about 3 o'clock in the morning for Mars, so don't stay up all night. But if you're up around about 3 o'clock in the morning, look to the east-northeast after 3 o'clock, and you'll see this, what looks like a small red star coming up over the horizon. It's actually Mars, and as the higher it gets, the brighter it'll become, because when you're looking down low down towards the horizon, you're looking through more air, so things look a bit dimmer. It can even actually change their colour a little bit. So wait till it gets up a bit higher, and you'll see that Mars is actually about the same brightness as Saturn, but whereas Saturn has this yellowish tinge, Mars has a distinctly ruddy colour, somewhere between orange and red. About an hour after Mars comes up, about 4 a.m., you'll see Jupiter rising in the northeast. Jupiter you can't miss because it's much brighter than Mars and Saturn. It's not as bright as Venus at the moment, but it's big and bright. You really can't miss it because it's the brightest thing in that part of the night sky. So if you're up early in the morning, you should be able to see Mars and Saturn and Jupiter, which is really good. If you're in the evening time, you can see Venus and Mercury over in the west just after sunset. And that, Stuart, is the sky for July.
That's Jonathan Nally from Sky and Telescope magazine. And this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Space Time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.